So, welcome everyone. I'm Paolo Pellizzoni and will present my paper, High-Order Genetic Interaction Discovery with Network-Based Biological Priors. And this was a joint work with Giulia Muzio and Professor Carsten Bogward. So, as many of you may know, genome-wide association studies, also called GWASs, seek statistical associations between some genetic mutations, such as single nucleotide polymorphism or SNPs, and the phenotype of interest, such as a disease. And to do so, usually one has a dataset with some cases and some controls, and for each of them, one has their genome. Then one would usually perform a univariate test between single SNPs and the phenotype of interest, therefore obtaining the statistical significance of each of the SNPs. But actually, in many complex phenotypes, there's a phenomenon called genetic heterogeneity, as described, for example, in Cordev, for which multiple mutations at different loci can actually have the same direction of effect on the phenotype. And therefore, considering combinations of SNPs can actually increase the statistical power of our tests and help us in understanding better these complex traits. And this is the focus of our work, considering combination of SNPs that are associated with the binary phenotype of interest. And to do so, we cast the problem in the item set mining framework. So let's look at an example to better understand this combination of SNPs. So again, we have our dataset with some cases and some controls, and the genome for each of our sample encoded, in this case, with the additive encoding. So if we consider as a pattern this position in the genome, then we say that the pattern appears if there is a mutation in that particular position. So in this case, the second sample has a mutation, and we say that the pattern appears. So in this case, we can see that there is a very faint association between the pattern appearance and the phenotype. If we consider another position, such as this one, then again, we have the pattern appears in the first and in the third position, and there is a faint association with the phenotype. But if we were to consider a combination of SNPs, so we say that the pattern appears if there is a mutation in either this position or this position, then we can see that this pattern appears in all of the first three samples. And in this case, there is a much stronger association with the phenotype of interest. So why is this problem difficult? Well, in typical GWAS dataset, we have at least 10 to the 5 SNPs, and the number of combination of SNPs scales exponentially. So if we were to test just single SNPs, the number of tests, of course, scales linearly with the number of SNPs. So in this case, just 10 to the 5 tests. But if we were already to consider just pairs or triplets of SNPs, then the number of tests would be exceeding easily the billions. And if we were to consider arbitrary combination, also arbitrary subsets of SNPs, then the number of tests would be a number so large that it doesn't even fit on the screen. So in this case, we would have a huge computational complexity problem and a huge multiple hypothesis testing correction problem. So in this case, statistics come into help. Indeed, for each combination of SNPs, there exists a minimum attainable p-value that is strictly positive and depends just on the pattern frequency. So we can exploit the so-called Taron trick to avoid testing many of these combination of SNPs, therefore reducing the number of tests that we perform. So the takeaway message is that if a pattern is very infrequent or very frequent, then it cannot be statistically significant. So in the limit, if a pattern never appears in the data or always appears in the data, for sure cannot be statistically significant. And we can couple this with the partially ordered set structure of our patterns. Indeed, if, for example, the pattern AB never appears in the data, then also ABC, ABD, and all of this branch will never appear in the data, so we can prune this portion of the search space very efficiently. But actually, even with this space pruning technique that I described you before, the number of combination of SNPs that we would test is still too high to be feasible. So previous work addressed this by restricting the search space that they look for. So for example, in FastCMH, they just consider contiguous interval of SNPs. So the number of combination that they consider is just quadratic in number of SNPs rather than exponential. And more recently, CineMin considered pairs of contiguous intervals belonging to interacting genes. Now, the limitation of these works is that the patterns that they can discover might be too simple to capture some complex phenomena. So, for example, if there's some genetic heterogeneity that spans more than 2 genes, then these methods cannot find such patterns. Moreover, SNPs are usually represented using an additive encoding that can take 3 values, so 0, 1, or 2, depending on the number of minor alleles in the locus. But actually, previous work, so FastCMH and CineMin, only accepted binary encodings for these genetic markers. And so one had to binarize the data beforehand, either by knowing or by guessing which is the most correct way of doing so. For example, one can use the so-called recessive encoding that takes 1 if both alleles are minor, or the dominant encoding that takes 1 if at least one of the 2 alleles is minor. So our algorithm OGMINE, which stands for Higher Order Genetic Interaction Miner, solves these 2 problems of the previous work. First, by considering arbitrary k-tuples of intervals belonging to interacting genes, so extending CineMin beyond just pairs. And this group of interacting genes are provided by the user as a form of domain knowledge. And to do so, one can provide, for example, connected subgraphs from a PI network, or protein complexes, or pathways. In this way, we avoid the exponential growth in the number of patterns while still retaining a high expressivity. Moreover, OGMINE can accept directly the additive SNPs encoding and can test patterns with both the recessive and dominant encoding at the same time. So in this way, we have a more fine-grained analysis compared to the previous work that had to binarize the data beforehand. So then let's take a look at some of the patterns that can be found by OGMINE. So again, we have our GWAS dataset with some cases, some controls, and the additive encoding for the SNPs in their genome. Moreover, we have the user provided biological prior, in this case, a PPI network. And the genes of the PPI network cover our SNPs. So for example, this purple gene is mapped to these SNPs, the yellow one to these ones, and so on and so forth. So if we were to consider this connected subgraph of 3 genes, then one of the patterns that OGMINE will consider is, for example, 3 intervals belonging to these genes, denoted by this black line. And then we'll say that this pattern appears in our data, denoted by this function phi, if in at least one of these positions there is a SNP, with, in this case, the dominant encoding indicated by these ones. So in this case, we can see that in the first sample, there is at least one SNP, so the pattern appears, while in the second sample, there is no SNP, so the pattern doesn't appear. So in this case, you can see that there is probably no statistical significance in the association between the pattern appearance and the phenotype of interest. But we can look at another pattern. So for example, if you consider these 3 genes here, another pattern we can consider is this dashed line one with these 3 intervals. And in this case, we have that this is encoded using the recessive encoding. And we can see that the pattern appearance seems to be strongly correlated with the phenotype of interest. So this would be a pattern that would be returned by our algorithm. So, of course, we tested our algorithm, OGMINE, on both synthetic and real-world data to assess, for example, its statistical power and the running times. So for what concerns the synthetic data, we simulated some small GWAS datasets, some with some also simulated PPI networks as a form of a prior. And for what concerns the real-world data, we experimented with both an Italiana dataset from Atwell et al. And a musculus dataset from Nico et al. So let's take a look at the synthetic data first. So we experimented with OGMine, increasing at each step the size of the search space that we allow for. So for example, for k = 1, we look at intervals in single genes. For k = 2, we look at pairs of intervals in pairs of interacting genes. For k = 3 in triplets of genes, and for k = 4 in 4 tuples of genes. Moreover, we compare our method to baselines, so FastIMH and CNeMin, that basically correspond respectively to setting k = 1 and k = 2. So as you can see, setting k = 3 and 4, so allowing for a larger search space, yields a higher number of significant patterns. And moreover, the patterns that we discover have a lower p-value, so basically they're more strongly associated with a phenotype of interest. This is because, being more complex, they can adapt better to the ground truth. Of course, this comes at a cost in running times. As you can see, setting k = 3 and 4 is higher running times, and this is because the larger search space takes more time to be explored. It must be noted, though, that if we compare to FastIMH and CNeMin, when we are at the same search space size, so setting k = 1 and 2 respectively, we are roughly 2 orders of magnitude faster compared to them. And this is because of a smarter exploration of our search space. So moving on to real-world data, we experimented with this Italiana dataset, and again compared to CNeMin and FastIMH. So as you can see, our method, OGMine, discovered the highest number of significant patterns in the data, many of which could not be found by some previous methods. Moreover, the patterns that we discover are the most significant ones. For example, on this anthocyanin 22 phenotype, the most significant pattern that we find is in this interaction of 3 genes and has a p-value of 1 × 10⁻⁸. While CNeMin finds a pattern that belongs just to 2 interacting genes and has a weaker association with the phenotype, so with a p-value of just 5 × 10⁻⁸. And by contrast, FastIMH even fails to find any significant pattern. This can be also observed on other phenotypes, for example, this LY one, where OGMine finds a pattern with a p-value of 1 × 10⁻⁸, and CNeMin finds a pattern with a slightly lower association with the phenotype, and FastIMH with an even lower association with the phenotype. So this dataset was obtained from an inbred population of Italiana. So the additive encodings are already binary, and that is why we can compare to CNeMin and FastIMH. But actually, we also experimented on this muscular dataset that is obtained from an outbred population of mice, and so the additive encodings actually can take 3 values. So in this case, we can utilize OGMine to its full potential. Indeed, if we look at the combination of SNPs that we find, for example, the first one, well, the first SNP belonging to the first gene is encoded with a dominant encoding indicated by the bold writing, and the second one is encoded with a recessive encoding. And this yields a p-value of 10⁻25. If we were to binarize the data beforehand, such as what FastIMH and CNeMin do, then with a dominant encoding, we would get a p-value of just 10⁻⁹, and with a recessive encoding just of 10⁻12. So with a much weaker association with the phenotype. And this is even more evident in this last pattern that we find that spans 3 genes, 2 of which with a recessive encoding and 1 with a dominant encoding. And if we were to encode them incorrectly just with the dominant encoding, all of them, we would basically get no statistical significance at all. So the conclusion of Gemine allows us to find a combination of SNPs that are statistically associated with the phenotype of interest, and our search space is driven by some domain knowledge provided by the user. So for example, providing PPI networks or protein complexes or pathways. So in the future, we'd like to improve the runtime performance of our algorithm, for example, by using some tricks from the item set mining literature and increase the statistical power, for example, using FDR control. Moreover, it would be interesting to apply our method to some novel real-world GWAS datasets and see if we can find some new interesting discoveries. So with this, that's all. Thank you for following, and you can contact me at this email, and you can check our code on GitHub.